So Monday, what were we talking about? That's actually today. So Monday we talked about, what's that? Several variables. So we got into 3 variables specifically. We could go more, but we'll keep it at 3 because that's the first step. Now we're going to talk about partial derivatives, and we're in 3 dimensions, right? So that's the important thing is we're going to look at things you learned in MAT211, the calculus, but we're not applying them to 2 dimensions, x and y. We're applying them to 3 dimensions, x, y, and z. Okay, so we're in a world where we don't have lines or curves, we have surfaces. So maybe this hand is like a bad example of a parabola. So this would be like an x squared. So my derivatives can kind of go in multiple directions, right? They will change along this sort of, we could, I guess, call it a surface curve. But that's a big thing, and we got to take a step. We're not looking at a line or a curved line or anything like that. We're looking at surfaces. So what we're going to do that actually, which sounds complicated, right? We got 3 things. It's like I can do this with 2 balls, but I can't put the 3rd ball in there. You need to be a juggler for that, right? That's a hard thing. But what we do to get past that is we are going to fix. So we got 3 variables. We'll fix 2 of them, and then we'll look how one of them changes. We're going to look at that derivative today of that one change. So we started it on Monday just looking at values, function values. So as x, y, and z change, we fixed pretty much 2 of them, or at least one of them, and then we could change the other one, and then it would give us an output. We're going to do the same thing, but remember, what is a derivative? What does a derivative give us? Does it give us a value? Like if it's a cost function, does the derivative give us a cost? No, it doesn't. It gives us how the cost is changing. So the derivative is always a slope, a rate of change. Okay, it sort of gives us a cost, but it gives us a cost per second, cost per minute. It gives us a rate. So it doesn't tell us necessarily where we are, it tells us where we're going. We also call it a marginal because it's a good estimate to go one more. We could use it for 2 or 3, and sometimes those are good estimates, but they really are, the further out we go, the more of an estimate it is. So in math, we limit it, it's a really good estimate for the next one, so that's what the marginal is. And in certain situations, it might be a good estimate for 2, 3, 4, or 50 down the road, but not always. Sometimes we're way off there because we're on the tangent line, right? We're not on the curve anymore. The curve might be going down. The tangent line is going to point out this way. We're way off course if we follow that tangent line too far. But we're usually okay to go one more. So that's the lesson today. We're going to take a derivative of 3-dimensional space. That does give us a tangent line. It gives us a rate of change, and it gives us a marginal. Okay? And we do this by fixing all the others, which will make all of this much more doable. And so I'm going to focus on a lot of different examples. What I did is I looked at the homework, but I decided if I just do the homework problems as examples, they're too close to it. So I went to the textbook, the ebook, and I pulled out similar type problems that are different enough but similar enough, if that makes sense. So let's go. So today we are in partial derivatives 15.2. I can't remember. I didn't look ahead what I had scheduled for Friday, maybe a quiz or something or activity. We'll do 15.3 on Thursday to kind of get us on track, which is some sort of like application of partial derivatives, okay? So let's kind of get into this. So partial derivatives. So here's the definition of partial. So if f is a function of x, then its derivative, df dx, measures how fast f changes as x increases. So it's a slope, right? As x increases, what's happening to the output really is what it gives us. It gives us a marginal. If f is a function of 2 or more variables, we can ask how fast f changes the function itself as each variable increases while the others remain fixed. So this is kind of like we're taking us, like what we did on Monday, we had to fix one of them so that we could then sort of see the slice of how the other one was doing. So we're going to fix everything except for one variable, see how that changes. That we can do. And these are what they call partial derivatives, because remember, we really have three variables in here, x, y, and z. We're going to fix two of them, and then we're looking at how one of them changes. So it gives us partial change. And then what we can do is we do it like for a particular point, we can take the partial derivatives of all three, and we can see how each of those variables is changing. And I think I copied in a nice application that where we could put our heads around it. So since we're taking derivatives, how many of you feel really comfortable taking derivatives? Maybe. Okay. A little bit. Some might need some practice. So you may need to go back a little bit, but let's go for a few simple derivatives. We don't have anything too complicated, but if I had, let's do a little bit. Okay, that'll work. And I want to go back. So let's just use it like f of x, or what, y equals x squared. How do I take the derivative of y? So I can list that as dy dx. What do I get? 2x. So the exponent comes down, just sort of remember the process. So that comes down in front, becomes a 2, and then we subtract 1 from the exponent. So that's one method we're going to use. So yes, that gives us that the derivative is 2x to the first power. Okay, so that's a simple one. What if I just had y equals x? What is that derivative going to be? Dy dx, derivative of x. The 1 comes down. So remember, I'm really doing the same thing. 1 comes down, I subtract 1 from the exponent. That's 1x to the 0, but anything to the 0 power is 1. So this is just 1. So we get, when we see just x to the first power, the x basically goes away, but sometimes if you think that way, you're going, well, what happened to it? It became x to the 0, so it's 1. So it's just going to be the coefficient in front. Okay? And let's do one more. What if I had y equals 3x? Then its derivative is going to be 3. Again, the derivative of x becomes 1, so this is just 3. One more variable, one type of derivative the other one we have to take is, what if about y equals e to the x? Remember, this is a very simple, it is e to the x. It's its own derivative. Okay, we have a few examples in here where x is something a little different, so we have to use the chain rule, but I think we'll just do that with x, with the explanation. So there's a few, there's a couple in here with chain rule. Okay. Also, we took the first derivative. How do we take the second derivative? Remember what the second derivative is? It's the derivative of the derivative. So nothing really new. It's just, oh, our starting point is different. So in this case, a second derivative, we would start, say, with this one, 2x. So the second derivative is just going to be 2. Okay, so it's just, think of it, oh, this is now our function, let's take a derivative. So don't think too much about, but the second derivative is something different than rate of change. That's the basic thing. It does not relate to the original function like the first derivative. Okay, so we've got 2 problems in the homework where we have to take a second derivative, a second partial derivative. Okay, so these are kind of the things you need to remember, get back in your, so we're going to be doing some of these. If it's not real comfortable to you, go, oh, I don't remember how to take that kind of, go back and review. I've got on my, if you go to any of my videos, they're on YouTube. You can link back to my MAT211. I've got all the video lectures from there. Not that you have to review the whole course, but they might be helpful in reviewing how to take a derivative. Okay, or you might, but that's what we're doing. So we have a little different notation. Instead of dy dx, we're talking about functions. So they use this, it's a Greek letter, which I don't know what the Greek letter is called, but it's the partial derivative. So instead of a d, they use It's probably the Greek letter for D. I don't know. But this will be a symbol that you'll see in the textbook. I'm going to show you in the next slide another notation that I use. It's a little bit easier. But this is the partial derivative with respect to x. This is the partial derivative with respect to y. When we take the partial with respect to x, what we're going to do is we're going to make y a constant. Now, we don't plug in a number, but we think of y as being a number. So if you take a derivative of a constant, what do we get? Oh, that's the one I left off. Derivative of a constant of a number, like what's the derivative? It's 0. Derivative of 10 is 0. Derivative of a million is 0. Any constant, its derivative is 0. So you're going to see when I'm taking the derivative with respect to x, I'm doing that partial derivative. Anything with a y by itself is just going to become 0. It disappears. I like that part. Okay, so we'll see that this actually, I was doing some last night because I remembered, I didn't understand it when I took 40 years ago, when I took partial derivatives for the first time, they didn't make a lot of sense. As I went through last night, oh yeah, they're not that bad. They're not like implicit derivatives. This is just a picture. They showed this a little bit later on. I don't want to get into too much detail, but I just wanted to remind you, we're in 3 dimensions, right? X, Y, and Z. So what we have is this sort of plane, but when we take its derivative at a point, we are getting a tangent line at that point that tells us where we're going. Notice it doesn't follow the curve anymore, but it projects where we might get just following that rate of change, okay? So that's just kind of don't try to understand all of this, but this would be the partial with respect to x. The partial with respect to y would be a line going in the y direction. It would be probably different. And then we could even get the partial with respect to z, and that would be a different sort of thing based upon these curves. So that's kind of what's going on. And remember, you can always go to Desmos /3D to pull up a 3D version graphing tool to kind of see what things look like, and then maybe it might make a little more sense. Okay, so here's an example. I didn't want to get too much into it, but let's see how partials work. So if this is our function, again, we're given a function, they want the partial with respect to x. Wait, where is, I thought I moved, well, maybe I moved it after this. Anyway, I'm going to use a little different notation, so I'll introduce it. Another way to write this is the way I kind of like it. It's f, and then I just put the little x down here. That's my way of writing, and it's another way of writing. You'll see it, f of x. So this is telling me I want the partial with respect to x. It's a little cleaner notation than writing this little fraction thing. So that's what I'm going to use. When I take the partial with respect to x, I take x and I take its derivative. So we just did this, right? The 2 comes down. You subtract 1 from the exponent. 2 minus 1 is 1. So that gives us 2x. And when I'm taking the derivative with respect to x, I just treat y as if it were a constant, a number. I don't put any number in. I could if I wanted to, but so y is a number. I square it. When I take its derivative, I get 0. And that's that part there. So the partial with respect to x is just 2x. So notice how I just treat y, I'm really working with just one variable at a time. Okay. When I take the partial with respect to y, which I could say here's the function, I'm going to take the partial with respect to y, so now I put the little y down there. That's my notation I'm going to use throughout the rest of this lecture, because I can't write this symbol very well for some reason. It's always sloppy. Again, in this case, the x is 0, but the y is 2y, so that's our partial. Okay. And remember, those are rates of change. Those give us a marginal. So we could predict whatever x and y is, that what would one more cost. So in this case, whatever x is, we could plug in x, and 2 times that, that would be our marginal. That would be our predicted next cost. Whatever y is, we plug that in, 2 times y. That gives us our next, our marginal cost. Okay, the cost of one more speaker, or we'll get into some examples. Okay, but that's all there is to this. Yes.
So in the first one, can we make y 0 so that we can find x?
Yes, in a sense, what you're thinking, you're really thinking, okay, let's plug in let's fix y at some number, and a lot of times they'll give us a point. So if you wanted to, you could plug that in. Let's just say 12. Think of it that way. Now, when I take this derivative, 12 squared is, I don't care what it is, it's a constant. It's going to be, when I take its derivative, it's going to be 0. So that's exactly what we're doing, is we're fixing y at some value. Okay. But yeah, it kind of seems, if you don't put a number in there, it seems, well, y is still y, isn't it? Well, not when we're taking the derivative of x. Any other variable is considered a number. So when we take its derivative, we're going to see some examples. If we have x times y, that's going to be a little different, and we'll deal with that. Okay, and the same thing when we did x, we could have said, well, x is a number, and it could be any number. It doesn't really matter. Let's say 27 squared plus y squared. So when we take this derivative, 27 squared is some number. We take its derivative, it's 0. Okay, so that's what we are really doing, is we're taking the variables we're not talking about, making them numbers, so that when we take their derivative, we get 0. Okay, we okay so far, sort of? And we'll look at lots of examples, and it's kind of like one of these things you'll start to, here it is, this is my slide. So this is my notation. I had it in the wrong place, but I'm going to use this instead of writing this fraction thing. It's just easier for me. If you want to use it, you're welcome to use it. Just recognize that in the textbook, a lot of times they're using that more formalized notation. And part of the reason is calculus was developed independently, simultaneously in England and Germany, at least the modern. I'm sure calculus was done before in many other world places, and they probably had different notation. The German notation is more of the, I believe it's the German, Leibniz or some guy. Anyway, maybe he was French. But anyway, over in Germany, they use this notation. England, they use notation like that. So they just had two different ways of doing it. You choose which one fits you the best. Okay, the key part is, we take the partial with respect to x, we are getting a rate of change. We are getting a tangent line, right? We're going off the surface, but we're following a tangent line now. We are getting a marginal cost, which means if I make one more of those things, then the rate is going to go to that level. It can help me predict one more item. And we'll do a couple of, same thing with y. And again, what we're doing is when we do one variable, we hold the other variable constant. And if it's helpful for you, just plug in any number. And the cool part is it could be any number. And then just kind of see how it is, and we'll get there, okay? So y is just, when I'm doing x, I make y into a number. Typically, it disappears. When I'm doing y, I make x into a number. It disappears most of the time. Okay, so let's take a look at some. So now we're right into the homework part. This is, I took from the textbook. So if you go into your WebAssign, there's an ebook. If you click on that, you can go to the chapter, and they got problems. The cool part about this is, for all the homework problems, for all the odds, there's a little button to click, and it will give you the answer. So if you want to kind of get, before you start doing the homework, and maybe while you're doing the homework, you come back and say, oh, here's one that's very similar. What's that answer? And then this is how I learned a lot of math, is I learned it backwards. I'd work from the answer. How did they get that answer? Oh, they must have done this and this. I tried over here. Oh yeah, they did this and this. Or if it didn't work, then I'd go back. But learning by backwards constructing it. I know the answer. I know what the question was. Let's see how they got there. It's a good way to go. And you have that opportunity for all the odd problems. And I'm doing some of these odd problems, like this one. You could look it up. I'll do some of the even ones too. So this comes right from the textbook. So let's kind of do this. What they want us to do is they want us to get the partial with respect to x, partial with respect to y. Then they want us to take the partial with respect to x and plug in the point 1 and -1. X is 1, y is -1. So we'll get a value, okay? So we do this all the way through. So I'm going to do the first step. Let's take the partial with respect to x. Oh, I guess I don't need a parentheses around it. It just feels, maybe I better not do that because that's more function. That's like f of x, right? Just f. So that's my partial with respect to x. So I look above, 3x squared. The 2 comes down. 2 times 3 is 6. There's my x. I subtract 1 from the exponent. 2 minus 1 is 1. I'm actually going to put it there. Don't have to, but it's kind of good. When I get to y cubed, what is its derivative going to be? Awesome. You're getting it. You got it, right? Y is now some number. We don't care what it is, but it's a constant. When we take its derivative, it's 0. I'm going to go ahead and put that in there just to emphasize that it just didn't disappear and evaporate. It became 0. What's the derivative of x? 1. What's the derivative of -1? 0. And again, so I simplify it a little bit. My derivative is really just 6x plus 1. Easy enough? Not bad, not bad. I kind of like this. Let's do it with y now. And remember, all we're doing is we're going to treat each x variable as a constant. So those are going to disappear. Each y is now a variable. So I come up here. What is the derivative of 3x squared? 0, because x is a number now, right? So I plug a number in, whatever, but its derivative is just 0. I like this part. 0 is like one of my favorite mathematical numbers. I get to y cubed. Now y is truly a variable. The 3 comes down, so I get and I subtract 1 from the exponent, so I get 3y squared. No big deal, right? I come over to plus x. What's the derivative of? It's 0. See, you're picking it up. X is just a constant. That's 0. And -1 is a constant, so that derivative is 0. Wow, this is cool. Remember your negatives. I sometimes forget those, so that's our derivative there. Next step, I think I've got another one over here, so I may have used up some of my space. But if I want the derivative with respect to x evaluated at 1, -1, what I do is I take my 6x plus 1, and everywhere there's an x, I plug in 1. Everywhere there's a y, I plug in -1. Oh, but there's no y. So what do I do with the -1? I just leave it alone. There's no place to put it. So the derivative at this point with respect to x is going to be 6 plus 1, which is 7. So that's a marginal. So whatever x represents, let's say it represents the cost of making one of those little yellow peeps from Easter. Easter's coming up, right? I don't know. I just made this up. But so we made 100 peeps. Making one more is going to cost us 7 cents. I was going to say $7, but that's a little bit much for a peep. So it's a marginal, whatever the units are. Okay. So it's telling us after we made this many, well, actually, this point is telling us we just made one. To make the second one cost us 7 cents. Let me get it in the context because they gave us x is 1. So we made one. So to make the second one is $7. That or 7 cents. That makes sense? Okay. Exactly. It not only almost, it is. It is marginal. It is marginal cost stuff in 3 dimensions. Exactly. And we'll do ones we did with the speakers, and they do the marginal cost and all that stuff. So same thing with the derivative of y at that point, 1 minus 1. The thing is, our function is minus 3y squared. So let me change colors. I plug in the y value, which is -1. There's no place to put x, so I don't worry about it. This is what's going to give me my answer. -1 squared is +1 times -3 is -3. So if y is something else, I don't know. I can't even make up things, but it would be the cost of 1 more y. We were at -1, so I guess we were in the hole. So whatever that means. But it's the marginal, it's the rate of change that we're doing with y. So y is going down by 3 if I go one more step in the y direction. X is going up by 7 if I go one more in the x direction. That's the way to think about it. Whatever the variables are. Okay, ready to get a little bit more complicated? Not too much, but a little. Yeah, so this is going to be an interesting one because this is going to be where something's a little different, but not too much. Let me give myself a little more space here. I'm going to erase these guys. It's still in the video. I am recording. Oh yeah, I'm recording. I hate this when I get 24 minutes in and I forgot to record, right? I'll have to do it later. Okay, so let's do this one. And maybe we'll just focus on taking the derivative once we got the derivative, that's where we plug the points in, but we'll see. Okay, so the derivative with respect to x. So 10,000 is just a number. Its derivative is 0. I'm going to leave it off just for cleanse. Derivative of negative 40x, that's got an x in it, so I can take its derivative. Negative 40x is negative 40, right? X to the 0 if you want. Derivative of 20y, 0. Good. You guys are fast now. Yeah. This is 0, so that's gone. How about, this is going to be the challenge, 10xy. 10y, because y is like a number, so it goes with the 10. It's just a constant. Exactly. Okay, so that was the harder part, but you guys, some of you picked up on that. That y just stays because it's a constant. The 10 stayed because it was a constant, because I'm taking the derivative of x, right? So x is 1, 10y is left behind. I'm not really taking the derivative. Now, when I use, it's a little more complicated because I should use the product rule on this, right? When I use the product rule and take the derivative of y, that part is 0. So I don't want to, but in this, we're not going to have too much problem with that. It's right. But the product rule, you take the derivative of x, we get 10y. When we take the derivative of with respect to y on this one, since we're focusing on x, that part's 0. So there is a product rule here, but notice how it's sort of clean. Product rule. We okay with that. Any questions? Please, if you do, even if you don't know what the question is, say, that's not quite clear. I'll try it. Okay. So let's see also if we take the derivative with respect to y, 10,000 is still 0 because it's a constant. Negative 40x is now a constant, right? That's 0. 20y is now 20, right? Y to the 0 if you want, but that's what that is. Now when we get to the 10xy, take the derivative with respect to x, that's 0. But when we take the derivative with respect to y, what's left behind? 10x. Okay. Beautiful. That's one of the more challenging ones, is because we got x and y multiplying. But so we still got them left. Now when we go with x and we want to find it at 1, negative 1, and again, we could do it at any point, we take our negative 40 plus 10, but now notice there's no place to put the x. There's only a place to put the y. And so this is negative 40. 10 times negative 1 is negative 10. It's going to be negative 50. Okay. And again, but remember this negative 50, even though we were plugging in because there was a y left here, this is, I keep putting parentheses, I apologize, I shouldn't do that, but this is the derivative with respect to x. So this is how x is changing. If I do one more x, so if I go to the second x, it's going to increase by 50. Negative, no, it's going to decrease by 50. Okay, negative 50. Make sense? That's our marginal. And then again, if we do with respect to y, 1 to negative 1, we take our partial derivative, we plug in x here, 20 plus 10 will give us 30. Okay, so there's going to be a number of problems where we're just going to need basically be able to do this. This part, the second part that they ask us to do is relatively easy because we're just plugging in the x and y values where they are, getting a number, and we're good. Okay. So far, so good? Okay, so going a little bit more complicated. This is a thing we added, so you'll have some of those. Let's see what else we got up our sleeves. So here's another one. Oh my goodness. All those variables, all those exponents, but not a big deal, right? It's really just the same thing we did. Each one has an x, y. So we'll walk through this one, getting a little bit more practice. Again, we're going to take the partial with respect to x. Y is a constant. Okay. So this first one, we look at the x. What's the derivative of x squared? 2x to the first power. What about this y to the third? That's a constant. It's not, we're not taking its derivative yet. We're still taking the derivative of x. This is sort of a product rule thing. So if there was a number like a 3 here, we would have taken 2 times 3, right? That's what that y to the third is. It's just a number. So it tags along. This is times y to the third. Now, thinking of product rule, when I take the derivative of y in this case, since I'm focusing on x, that derivative is 0. So that's why I don't see the product rule here, is the second part of the product rule. When I do that, it's 0. Okay, so that was, you're on the right track there. Good. So far, so good. Let's try another example. This one in the middle is exactly the same. What do I get when I take the derivative of x to the third? 3x squared. What is y squared? It is a constant, so y squared. Cool. What do I get when I take the derivative of xy? Well, that's x is 1, y is just a constant, so it's just y, 1 times y. We okay with that? So you kind of see this has multiple levels. Now when I go for y, the same thing's going to happen, but x is going to be the constant, y is my variable. So I'm taking, in this first term, x to the third. Actually, I don't even need to think product rule, really, because x is a constant. Y to the third is what I'm taking the derivative of. The 3 comes down. I get y squared. And the x squared just tags along for y, because it's a constant. Okay, right? It's just like if it was 5, I'd take 3 times 5 and put 15. But I don't know what number it is. It's really just x cubed. It stays there because it's a constant.